Hello, everyone. It is an honor to present our research titled, A Hybrid DRL and GenAI Architecture for Adaptive Tutoring of Vector Spaces in Virtual Reality. I am Pablo Ordóñez, and alongside Dennis Macas, we explore the future of immersive tutors in math education. Higher education faces a critical challenge: overcrowded classrooms and very high student-to-teacher ratios. This makes personalized feedback almost impossible. In subjects like linear algebra, this lack of individual tutoring becomes a huge bottleneck for deep learning. Understanding vector spaces imposes a massive cognitive load. It demands abstract spatial visualization skills that are rarely built by looking at a traditional whiteboard. We need environments that materialize these abstractions, but also possess the intelligence of a human tutor. Artificial intelligence offers answers. Deep reinforcement learning models, or DRL, are masterful at inducing optimal long-term pedagogical policies. However, they suffer from semantic blindness. They select discrete mathematical actions, but cannot generate language or explanations for the student. On the other hand, large language models, or generative AI, communicate wonderfully. They generate empathy and fluency, but they operate reactively and lack long-term strategic optimization based on student states. Leaving them alone increases the risk of instructional hallucinations. Our proposal to solve this is semantic decoupling. We modularize the system by separating the strategic intelligence handled by a DRL agent from the communicational intelligence managed by Google Gemini. The DRL decides what to do, and Gemini translates that decision into spoken feedback. We brought this intelligent engine into a virtual reality environment developed in Unity. We rely on the theory of embodied cognition. We turn an abstract and static calculation task into a fully spatial, physical, and motor interaction that facilitates memory retention. The core mechanic requires users to select their answers by physically drawing and shooting a virtual bow toward floating targets. Leveraging body movements to solve spatial problems immerses the student, protecting their motivation while they interact with a mathematical problem. From a pedagogical standpoint, our tutor implements Vygotsky's scaffolding theory. When the student fails, the system provides structured help across 3 sequential levels. The goal is to deliver strictly the necessary cognitive support so they can progress without creating dependency. If a first mistake occurs, the tutor gives a conceptual hint. If there is a second failure, it gives a specific procedural hint. If they fail a third time, it explains the problem step by step. All this is verbalized empathetically by our avatar, thanks to Gemini. Technically, it works as a client-server architecture. Unity manages physics, rendering, and voice on the MetaQuest 2. After each answer, it sends telemetry data to a local Flask server, where our PyTorch DDQN engine resides, connected to the Gemini API. The server feeds our DDQN neural network with the student state, their historical accuracy, response time, and attempts. Based on this, the network makes a purely mathematical decision to facilitate the next challenge, maintain the difficulty, or increase the challenge. That discrete decision is injected into a structured prompt towards Gemini, along with the mathematical context of the mistake. Gemini acts as a linguistic interface, taking a cold command from the algorithm and transforming it into coherent and mathematically accurate spoken feedback. To validate this architecture, we ran a pilot test at a public university with 9 computer science students in 20-minute sessions, processing a total of 156 tutor interventions. Additionally, we gathered an expert panel of 2 university math professors for coherence evaluation. We evaluated the DDQN model against an expert gold standard, revealing that the algorithm always converged to facilitate the tasks. It showed a 33.3% match, revealing a suboptimal policy due to domain transfer from a propositional logic environment. However, here is the fascinating part. Even though the decision-making algorithm was suboptimal, the agreement evaluated by the experts was perfect, a Cohen's kappa of 1.0. Furthermore, overall student satisfaction was very high, scoring 4.66 out of 5. This contrast between the technical failure of the DRL model and the extremely high student satisfaction proves the enormous pedagogical resilience of semantic decoupling. Gemini's generative layer acted as a safety net, protecting user motivation against the initial strategic deficiency. For educational technology, this is vital. It allows us to deploy artificial intelligence without the risk of uncontrolled hallucinations. Generative AI is limited to communicating only what a mathematically auditable model tells it to, combining the best of both worlds. Our next steps include expanding the statistical sample and natively retraining the DRL model with linear algebra data. We will also aim to conduct quasi-experimental studies with control groups to empirically measure the effect size on students' cognitive learning outcomes.
Bienvenido al tutor inteligente de matemáticas. Este sistema te ayudará a practicar y mejorar tus conocimientos a través de ejercicios adaptativos. Antes de empezar, recuerda cómo usar los controles. Utiliza el botón de agarre, en rojo, para sostener el arco con una mano. Luego, con tu otra mano, usa el mismo botón de agarre para tomar una flecha y tensar la cuerda. Te puedes mover con el joystick izquierdo en color verde. Ahora, escucha con atención antes los ejercicios que vamos a comenzar. Dado el vector, igual a 1,4 en R2, ¿cuál es el resultado de la operación 2 por? Correcto, resolviste el problema en el intento 1. Dado el vector v igual a 2,-1 en R2, ¿cuál es el resultado de la operación 3 por v? Incorrecto. Te quedan dos intentos. S. Recuerda que al multiplicar un vector por un escalar, debes multiplicar cada componente del vector por ese escalar. Incorrecto. Te quedan uno intento. S. Aplica el procedimiento paso a paso. Has agotado los 3 intentos. La respuesta correcta era el vector 6, menos 3. La solución se obtiene siguiendo la definición matemática del concepto. Dado el vector v igual a menos 1,5 en R2, ¿cuál es el resultado de la operación 2 veces v? Correcto, resolviste el problema en el intento 1.